This week we're going to start our discussion about statistical inference, which is the second half of our statistics course. And this is where we start taking a look at sample data and using it to make inferences about the population from which that sample was drawn. We're going to start that conversation with statistical estimation. And it turns out in stats, there are two ways to estimate a value. We can use something called a point estimate, which is that is not what I meant to do, a single value. In other words, based on prior studies, we might believe that the standard deviation in student height is 1.6 inches. And you'll notice we are giving a single value for a population parameter based on sample data from a previous study. This is nice in that it's fast to do. We already know how to calculate those single sample statistics. So that's something that's quick to do on a calculator with one var stats. The downside is that a single sample is unlikely to produce an accurate estimate. The other option is to use an interval estimate, which provides a range of values. For example, based on our data, we might believe that the student mean height is between 59 and 62 inches. And the nice thing about this interval estimate is it gives us a little bit of wiggle room. We're acknowledging that our data pulled from a single sample is unlikely to perfectly reflect the population it was pulled from, and so we're giving us a margin of error, kind of hedging our bets in using that sample to estimate the population. So these estimates are used to estimate an unknown population parameter using sample data. And this is one of two ways that we do inferential statistics. The first is we use sample data to estimate an unknown population parameter. The other is that somebody else has made a claim about a population parameter, and we use sample data to test the validity of that claim. So estimation and then testing claims are kind of the opposite. We're going to start with estimation this week, and then we'll start looking at a variety of tests to test the claims that others have made over the next couple weeks. In general, when we talk about point estimates, the best point estimate for an unknown population parameter is the equivalent sample statistic. What that means is if I'm trying to estimate a population standard deviation, the best estimate I could get is the corresponding sample standard deviation. If I want to estimate an average height for an entire population, the best point estimate I could do would be a sample height from that same population. And we have an example here. It says, find the appropriate point estimate for the population height of Rancho San Juan students based on the sample data shown below. And there's a list of some heights of students at Rancho San Juan that I collected as part of an AP statistics activity. And I know that if I'm trying to estimate the population mean height, the best way to do that would be to use the sample mean. And we know to pull sample mean, we're going to go data into list 1, and then 1 bar stats. So a skill from way back in week 1. So we're going to put our data in a list, stat, enter. And then we're going to go stat, calc, 1 bar stats. And since I only have data in list 1, I want to clear out my frequency list. And we get a sample mean of 64.52 inches. So the best point estimate for mean height at RSJ would be 64.52 inches. So if you're asked for a point estimate for a parameter, find the sample statistic that matches it. We very rarely use point estimates by themselves, but they are tied to the next type of estimate. So the other type of estimate is called an interval estimate. And the interval estimate we're going to be using in statistics is called a confidence interval. Confidence intervals use the appropriate sample statistic as the center of their interval. Meaning the appropriate point estimate becomes the center of our interval estimate. If I'm estimating a mean height, that sample mean height is going to be the center of the interval that I build. The width of the interval is then determined by 2 things. How confident we want to be that the interval contains the value that we're trying to estimate. The more confident I want to be, the wider I want that interval to be. Think of it like darts. If I want to be sure that my dart is going to hit the board, it's easier if I have a bigger board, particularly for me who is wildly uncoordinated. Intervals in statistics work the same way. If I want to be more confident my interval contains the correct value, I want to make my interval wider. The other thing that's going to determine our width is how spread out the sample data values are. So we're going to be looking at measures of spread, namely standard deviation. Data values that are more spread out will result in wider intervals. Sample data that is more clustered about its mean will result in smaller intervals. And in our next video, we're going to take a closer look at how these things influence the structure of confidence intervals. As usual, if you have any questions, you can reach me via email at any time. Otherwise, I have office hours on Thursday and Saturday. Please let me know if you have any questions. Otherwise, I'll see you in our next video.